Today, I'm going to teach you a very powerful technique, how to calculate value to bluff ratios in poker. This technique lets you understand how often you should be bluffing, but also how often your opponents ought to be bluffing if they were balanced. Let's get started. Many players learn the basic bluff value ratios on the river, but poker is not a one-street game. You're not just playing a river. There are multiple betting streets, and each street compounds these effects, allowing you to bluff more and more often, assuming you're using a polarized range. So in today's lecture, we're going to go over understanding the concept of indifference. We'll talk about the theory of leverage. We'll talk about how to calculate value to bluff ratios on the river. And finally, we're going to work backwards from the river and show you how this works in a multi-street game so that you can calculate these numbers on the turn and the flop as well. Let's start by talking about indifference. Indifference in poker means that two actions have the same value. For example, if you have a bluff catcher that's right on the edge of the line facing a bet, your hand might be indifferent between calling and folding. If you have like a thin value hand, it might be indifferent between checking and betting. And all indifference means, again, is that two actions have the same value. So the reason we understand indifference is to find balance. And the goal of balance is not by itself to be balanced, but rather to understand where the line is, to understand what balanced play looks like in a vacuum. When you understand where the line is, you have a baseline from which to deviate if your opponents are, for example, not bluffing enough or bluffing too much. And in contrast, you'll also see where your own leaks might be. To understand bluff to value ratios, we need to understand how to solve a basic polarized river toy game. So here, hero has ace-ace or queen-queen. They have value or bluff. Villain holds a bluff catcher. There's a half-pot bet. We can either shove or give up with our queen-queen sometimes. So what is our best strategy? To solve this is pretty straightforward. Of course, we always want to value bet our ace-ace, and we need to bluff enough to prevent villain from always folding. Otherwise, our value hands don't get paid off. At the same time, if we bluff too much, then they can snap call all the time, and now we're losing too much money with our bluffs. So the correct amount of bluffs sits somewhere in between. If you do the math, you'll find that the correct bluff percentage on the river is always equal to the pot odds laid. In this example, we're betting half pot. What that means is that villain is getting pot odds of 25%. They need at least 25% equity in order for their kings to break even after calling. If we bluff less than 25%, well, in that case, they can always fold. And if we bluff more than 25%, then they should always call. Now, in practice, you're never going to get this just right. You know, who knows exactly how often you're bluffing in every spot, but you can develop a sense for it. A really simple way to go about this, on the river anyway, is to simply use a pot odds chart. So we've got this one here. On the left-hand side, you'll see the bet size as a percentage of the pot. And on the right-hand side, you'll see the value to bluff construction. And so, for example, for a half pot bet, we see that 75% of our betting range should be value and 25% of our betting range should be bluffs. And that's again because they need 25% equity to break even on a call. And therefore, if a quarter of our range are bluffs, then we make them indifferent between calling and folding. And you'll notice something here. The larger we bet, the more bluffs we can use. So if you bet 150% pot, well, in that case, villain has, let's see, they need somewhere like 37, 38% equity to call this bet, and therefore a larger proportion of our betting range can be bluffs. Now keep in mind that this is assuming a perfectly polarized toy game where our value hands are always the nuts and our bluffs always lose. In reality, your opponent might have some traps, and that's going to limit how big you can bet because you don't want to bet so large that you're only getting action from the few traps they have, right? So, returning to the toy game, our value percentage should be 75%. Our bluff percentage should be 25%, which matches the pot odds for a half pot bet. Conversely, villain should call according to the minimum defense frequency. which in this case is 2/3 of the time. Okay, let's see if you were paying attention. Here's a quiz for you. Villain bets 7 big blinds into a 10 big blind pot on the river. You shove for 25 big blinds. What is the optimal value to bluff ratio? Take a moment to consider your answer. The answer is B, 70% value, 30% bluffs. That's how often we should be value betting when we check, raise, shove the river. So the way you work this out is you calculate the pot odds of your shove. How do you calculate pot odds? Well, the equation is simply the amount they have to call divided by the pot after they call. So they need to call 25 minus 7 because they've already bet 7. So 18 more big blinds. And the pot after they call is 60 big blinds. 18 over 60 gives us 30. And therefore, they need exactly 30% equity to call. Now, if you imagine that we're raising the river with only nutted hands that always beat their value and bluffs that always lose to their calls, well, in that case, we need exactly 70% value. Okay, let's talk about the theory of leverage. Leverage is a really interesting concept. Now, this idea has been known for a long time. The way that these bluff to value ratios work, this has been known since mathematics of poker. I first learned it from Applications of No Limit Hold'em by Shonda. But Andrew Brokos, one of our writers, he wrote about it in his book, Play Optimal Poker. And he describes this phenomenon as leverage. And leverage is this compounding effect of you can use more bluffs on earlier streets as the bluff to value ratio compounds. And so the way he words it, leverage is the additional value gained from betting hands that you anticipate profitably betting on future streets. So hands that can bet multiple streets as part of a polarized range benefit the most from leverage, especially deep stacked. If you want to learn more about leverage, we have this article, What is Leverage in Poker? Link in the description. It's a good intro to this concept. Let me give you an example of leverage. So imagine that you're playing a hand and you have a static bluff catcher facing a pot-sized bet on the turn. Your opponent is using a range of 20 nuts to 10 bluffs, so 2-1. How often should you call their turn bet? Take a moment to consider your answer. Surprisingly, the answer is 0. You should actually just fold everything. And this, I think, is going to be more surprising to the people that already kind of understand this topic, because if you look at the actual numbers, they have 2 value bets for every bluff, and a pot-sized bet lays what pot odds? 2-1. So if we only look at the immediate pot odds, we are getting pot odds to call this bet. And yet, the best move is to always fold. Why is that? Well, the answer is that villain is under bluffing, because it's not just a pot-sized bet. You see, let's think about this. They have a range of 2-1 value to bluff, 20 nuts to 10 bluffs. We have static bluff catchers. That is to say, bluff catchers that always beat bluffs and always lose to value, can't improve. There's a pot-sized bet behind on the river. What this means is that villain can always bet the river, right? Because they have the correct value to bluff ratio to pot the turn and then pot again on the river. And so essentially, we're not facing a pot-sized bet. We are facing a pot-sized bet and another pot-sized bet for a total of like effective 400% pot. And so what ends up happening is we are risking essentially $400 to win $500 if we call down both bets, starting with a $100 pot. For this reason, they actually need to be bluffing more often on the turn. And this is the concept of leverage. Without draws or implied odds or any of those other abstract terms, the simple ability to bet twice with a polarized range or bet 3 times allows you to apply leverage. Now, what I'd like to do next is visualize the money, but I can't quite do that just yet. First, I need to teach you guys about a misconception in poker. You've probably heard this idea that the EV of folding is equal to 0. Well, this is a fine way to look at it. It's just a convention we use to make the math easier. You see, other reference points are also useful. In fact, what most solvers do is they don't use EV equals 0. They use the expected value of actions is equal to the start of your stack at the start of a hand minus your stack at the end of a hand. So let me give you an example of what that might look like. This was one of the first articles I wrote for GTO Wizard, and it's called What is Expected Value in Poker? And over here, I wrote a section about EV relativity. And so here's an example. Let's say that you 3-bet ace queen suited on the big blind and you face a 4-bet from the button. You can either fold, call, or shove. Now, if we check the expected value of ace queen suited, we can see the expected value of folding is 0, calling is 4, and shoving is 2.5. And so calling is the best action. However, this is not the expected value we actually get from a silver. From a silver, it actually calculates this, assuming that your 3-bet was to 11 big blinds. And so again, we're choosing between 3 options and trying to choose the best option, which in this case is calling. But the actual amount of money you'll make relative to your stack is losing about 7 big blinds on average. Now, why am I teaching you this? Because using a common reference point is really useful for understanding multi-street EV calculations. This concept of folding equals 0 EV is great for one-street calculations, but it kind of fails miserably when you're trying to do EV calculations over multiple streets. And so you need to kind of let that idea go and use a fixed reference point for your EV calculations if you want to calculate multiple streets of betting. So with that EV perspective in mind, let's now visualize the money, because a lot of people don't understand how you can face a balanced bet on the turn, and yet it's a bad call. So let's take a look here. We'll start on the left-hand side. It's a $100 pot, a $400 stack, and villain bets $100 on the turn. We can either call or fold. If we call, villain will always bet the river. If we call again and we win, we'll win $500. That is the starting stack, so villain stack plus the pot. If we call and lose, we'll lose our $400 stack. Now, conversely, if we call the turn and then fold the river, we'll lose our turn call, which is $100. And the final option is to just fold immediately on the turn and lose 0. So this is our fixed reference point. Let's calculate how much money each line makes. And so if we calculate our equity on the river, it turns out to be minus $100. And so 1/3 times 500 plus 2/3 times 400 gives us a minus $100 river call. Conversely, folding is also worth minus $100. And so we're indifferent between 2 minus $100 decisions on the river. And you see, the problem is that they'll always bet the river. So if we trace the decision back to our turn call, we'll see that the best option was actually just to fold immediately and never see a river to begin with. And so this begs the question, why do we ever call down with a static bluff catcher? Well, how often should villain actually be bluffing the turn for this to make sense? And so let's add another diagram, and this time we've given villain a give-up range, and these are hands that will bet the turn and then give up on the river. When this happens, we're going to win the pot, $100 plus their turn bet, so a grand total of $200. And if this happens often enough, we can recuperate our turn bet. Again, if we calculate the expected value, we find that we need them to give up on the river at least 1/3 of the time and bet again 2/3 of the time. And in fact, the math works out such that their give up frequency on the river should be equal to our pot odds on the turn, regardless of the bet size. And so that's how you actually recuperate your money with a static bluff catcher. You recuperate it through villain giving up on later streets. And if villain is not giving up on later streets, that tells you that either A, they're over bluffing, they're just not taking their foot off the gas pedal, or B, they were under bluffing to begin with and never needed to slow down because they were too nitty to start with. Okay, so you understand how to calculate these value to bluff ratios for one street, and we've seen the power of leverage. Now it's time to understand how this extends to multiple streets. So how often should villain be bluffing the turn? If 10 bluffs wasn't enough. Remember, the stack to pot ratio is 4. We're facing a pot-sized turn bet, and there's another pot-sized bet behind on the river, and villain starts with 20 nut combos. How many turn bluffs do they need in order to be balanced on the turn? Take a moment to consider your answer. The answer is D, 55%. In fact, they should be bluffing more often than they're value betting on the turn in order for us to have a break-even call with our bluff catcher. And so this brings us back to the power of leverage. Here I've graphed the value to bluff ratio on the flop, turn, and river, and we can see they can use more bluffs on the flop than they can on the turn than they can on the river. On each street, we expect them to give up with a portion of their bluffs and bet such that they're balanced by the river. How do they construct their strategy? Let's walk through this step by step with an example. So again, let's imagine this time that we're hero and we're the polarized player holding either a value bet or a bluff. And just pretend that our value bets will always be value and our bluffs will always be bluffs, and their bluff catchers will always be bluff catchers. We start with 8 nutted hands and 37 total combinations. So 29 of those combinations are bluffs. We're going to fill out this table together to show you how to calculate value to bluff ratios over multiple streets. So first of all, in a perfectly polarized toy game, you always want to bet your value hands. So our value hands always bet flop, turn, and river. And the reason for this is that there's no reason to trap if you don't have any showdown value. So in this case, if we check, why would they bet? Just to fold out our bluffs and get called by any traps? No. Betting does nothing for them, so there's no reason for us to trap or to protect our range. So we're always going to bet our value. Okay, so we've got that column figured out. What about the bluff column? Well, we know on the river that, and again, we're using a pot, so we're potting all 3 streets. On the river, we should be bluffing half as often as we're value betting. We want to use 2 to 1, 2 value bets for every 1 bluff. And so we already know this column. But how often should we be giving up? Well, a give up percentage is equal to pot odds laid on the turn. And so pot odds laid for pot size bets are 33%. So we should be giving up a third of our range on the river. And that works out to 6. So 6 over 18 is 1/3, a third of the time we give up. Now that we know how many bluffs we have on the river, we know how many bluffs we have on the turn. 6 plus 4 is 10. And again, our give up range should be such that we're giving up a third of the time on the turn, which works out to 9. And again, 10 plus 9, that's 19. And that leaves the remaining 10 give ups on the flop. And so we can already figure out if we just know the total number of nuts and bluffs, how often we should be value betting and bluffing on each street. Let's visualize that. On the right-hand side, we can see a flow chart that shows how often we're value betting and bluffing each street, as well as our give-ups. Now, why did we calculate all this? What is the point? Well, the ultimate goal is very simple. We just want to get our value bets paid off as often as possible without becoming exploitable by over-bluffing. And so we arrive at the river with a perfectly balanced range of 8 value bets to every 4 bluffs, while simultaneously giving up just often enough to prevent villain from snap folding earlier. So the entire purpose of this strategy is to get your value bets paid off as much as possible. Now, you may be asking yourself, this is based on 3 pot-sized bets. However, you can calculate this for any bet size. It's actually relatively simple. Now, I have a simple spreadsheet application here, Caveman GTO calculator. You might have seen from some of my earlier work, but I've never actually explained how this works. The math is fairly straightforward. So for a perfectly polarized range, that is to say, value bets always win, bluffs always lose, the value betting percentage is just 1 minus the product of the pot odds. So for example, in the river, 1 minus the river pot odds is equal to the amount of value you should have, right? If you bet pot on the river, you're laying pot odds that dictate 33% bluffs and therefore 2/3 value. And so you can multiply it out. For example, in the turn, you can multiply out 1 minus the turn pot odds, multiplied by 1 minus the river pot odds, and that gives you the percentage of value that you should be betting with on the turn. And same thing for the flop, just the product of 1 minus pot odds. Pretty straightforward calculation. So let me show you the Caveman GTO calculator next. Okay, this is a pretty basic application. Again, we can enter any set of bet sizes here. So 67, 89, 152. It'll just calculate this out for you. So let's just go over the assumptions that we're making here. We assume that villain can only call or fold, which again, if we're perfectly polarized, they would have no reason to raise. We assume that equity is static, that we're balanced, and that there are no blocker effects. So this is a nice, simple toy game. I've also included sections here to add the equity of your bluffs and value bets. And this is a calculation that Jonda did in his work, Applications of No Limit Hold'em. In my experience, this actually does not work out well because the way he models it, he models a bluff, for example, having 20% equity, meaning that it always has 20%, no matter how much you narrow the opponent's range. Or conversely, if you have value bets, he would model that as this always has 80%, no matter how much we narrow the opponent's range, which isn't really the case in reality. So I'm not actually going to use that. I'm just going to use perfectly polarized equity. And here we can see the value to bluff ratios on flop, turn, and river. And so let's enter our pot toy game. And here we can see the appropriate value to bluff ratio says we should be bluffing quite a lot on the flop, less so on the turn, and less so on the river. Now, next, I'd like to show you how this actually works in GTO Wizard, and we'll compare the idealized caveman toy game to what the solver thinks we should be doing. But before we do that, we need to address the elephant, or rather the cow in the room. You see, the cow is a sphere. What this means is that we're trying to represent an extremely complex topic, which is Nash equilibrium in poker in an almost infinite game space, with a super basic toy game model. And this doesn't really match reality. Our equity is not static. Bluffs and value is a false dichotomy on earlier streets. And we can't perfectly plan out bet sizes. We can't just pretend that we know exactly what bet size we're going to use. And we can't pretend that we don't have showdown value in some of these lines. This is not how actual poker works, obviously. However, the reason we represent the cow as a sphere in physics, and the reason we use oversimplified models in engineering to represent more complex topics, is because it allows us to understand the inner mechanics behind how stuff works. And once you understand those inner mechanics, you can extrapolate those ideas and abstract them to more complex spots, to spots that cannot be calculated with standard handwritten calculations, as you could with this toy game. And so by using simplified models like this, we can understand spots more deeply and understand this idea of leverage and bluff to value ratios compounding on a better level. So without further ado, let's open GTO Wizard and see how the solver applies these concepts. Now, the beauty of this is that it works for all formats: MTT, cash, heads up, spin and goes, you name it. The math is universal throughout poker. So I've got 3 examples here. We'll look at an MTT spot first at 35 big blinds deep. For this first example, I've chosen a hijack versus button spot. So hijack opens, the button calls. Flop is queen 5-4 rainbow. Hijack c-bets, and we get a raise in position. This is going to give us a pretty polarized line that will match our toy game model quite well. Hijack calls, turn is the deuce of clubs. Barrel. Hijack calls again, and on the river we ship it in for the last 40% pot. Now, when button shoves, hijack has 22% pot odds, 22% equity to call, and therefore button should be bluffing 22% of the time. Just go over to the ranges tab, look at the equity buckets, see that 22% of button's shoving range contains bluffs. Exactly what we expect. Going to our toy game model, type in the bet sizes here. So raise 33% on the flop, barrel 55 on the turn, shove 40 on the river, and again, we see a ratio of about 78-22 on the river shove. What about the turn? How closely does that match? If we just go back to the turn, after we've put in the 55% bet, I just select the best and the good hands that button is barreling with. See that 58% of their turn betting range contains value bets. Again, our toy game model says 57%, pretty darn close. Lastly, if I go over to the flop, after button has raised, and this time instead of equity buckets, let's use hands, because hands is maybe a little easier to define this as the value bet. What does it say? 48%. So about 48% of button's flop raising range should contain value bet. Our toy game model predicts 46%. Pretty darn close. All right, for this next example, we're going to take a look at a cutoff versus big blind 200 big blind deep cash game. So cutoff opens and big blind calls. See a queen 4 deuce rainbow flop. Cutoff c-bets third pot. And the big blind hits him with a pot-sized check raise representing sets, 2 pair, and top pair. Cutoff calls, 9 of hearts turn. And the big blind continues to barrel, preferring this 125% overbet size. Cutoff calls. River is the queen of hearts, pairing the top card, and the big blind ships it in, representing a whole lot of boats. So, after the big blind shoves, there's a little thing here. We've just added this feature. This shows your pot odds. And so the cutoff's pot odds facing this shove are 38%. Going back to the start of the lecture, what does that tell you? Well, it tells you that about 38% of the big blind's shoving range could contain bluffs. And that's exactly what we see. Just select all of these bluffy hands, about 38%. Or we can select the value hands, about 62, 63%. So let's go over to our caveman GTO calculator to see if it agrees with us. We check raised pot on the flop, overbet the turn, and chipped it in on the river. So on the river, we would expect about 62% value. And that's exactly what we see. Now, again, it's not going to be perfect because there's some minor blocker effects, but this is pretty darn close. So let's go back to the turn. We've overbet 125%, action on cutoff, and I'm just going to select our value hands here. So again, these sets, these 2 pairs, these are clearly value. The only other question is, does top pair count as value? And so if we include these, we have queen 7, queen 6, queen 5, queen 3, some very marginal top pair weak kicker hands as a merged bet. And so then we'd have 43% value bets. And if you don't include some of those, then it's closer to 37% value bets. So somewhere between 37 and 43. And if we go over here, we expect in an idealized toy game about 40% value. So lastly, going over to the flop, after we've check raised pot, we can select, let's say, top pair plus as our value region. It gives us about 30.7. If you don't count some of the mergy top pair, then it's maybe closer to like 25%. And that's exactly what we see here. Now, you'll notice something else. We're very deep in this spot, which means that the big blind can overbet twice. And this means that they can bluff more. We can see that they only need about a quarter of their range to be value bets on the flop check raise. So the deeper you are, the more important the nut advantage becomes, because you can polarize much harder when you're able to bet much bigger. And that also means that a larger portion of your range can start bluff raising relative to the number of value hands you have. Okay, for our last example, we have a heads-up sit and go, 25 big blinds deep. The small blind starts with a 2 big blind open. And yes, I know if you haven't seen heads-up sit and go solutions, there is a lot of limping in position. That is just part of the strategy. So they open, big blind calls, and we get a low connected flop 6-4 deuce. The aggressor c-bets, and the big blind again check raises. And I'm showing you a lot of raising lines because these are quite polarized and will closely match our toy game models. Whereas here, it's very hard to tell where the bluffs end and the value bets begin. So they raise, and we get another low connected card, this time the 5 of clubs, which is actually pretty good for the big blind's check raising line. They have a lot of these low cards. This hits their check raise well. So they continue to barrel, this time 2/3 pot. And we get an ace on the river. And so the big blind shoves it in with a good portion of their range, representing mostly straights or nothing. Now, let's take a look at the value to bet ratio. So on the river, again, I'm going to use the ranges tab, and we're going to use Well, let's just say straights and maybe two pairs. Two pair value bet, it's hard to say. About 72% equity. That's approximately how many value bets they should be using on the river. Let's see what our toy game model says. Check raise 33% on the flop, 65% c-bet on the turn, 59% on the river. Okay, so on the river, we expect about 73% value bets. Okay, that makes sense for this size. This is the pot odds for a 60% pot size bet. And yeah, this is exactly what we see. Now, on the turn, we would expect to see about 52% value bets. So let's go back here. We'll head over to the turn. So we've barreled the turn, barrel. And again, let's just use, I don't know, two pair and straights as the value portion of this c-bet, which comes out to about 50%, 49.4. Call that 50% value bets on the turn for this bet size. And yeah, here it says 52%. So our toy game model predicts slightly more value, but the fact is we also block a lot of the straights when we have a straight, so that changes the calculation a bit, but we're ignoring card removal in our simplified model. And finally, on the flop, we expect about 42% value bets. Here, if we go back to the flop, okay, and we say, what are we check raising with? Well, let's see, top pair, two pair sets, all of these hands. So let's say top pair plus is our value region. That's about 39% of our overall check raising value range. And here it predicts 42%. So reasonably close. And you can see this concept of leverage is applied to all of these scenarios. And especially when I'm, cherry picking these very polarized lines, this toy game model works very well. And so the real takeaway here is that you need to be bluffing more on earlier streets, giving up a portion of your range, and knowing that just because you have direct pot odds to call doesn't actually mean that you should be calling. In fact, you should be bluffing quite a lot more on earlier streets, and so should your opponents. And if you're playing against people that aren't doing that, well, you know what to do. Let's summarize. So leverage is the phenomenon of compounding pot odds over multiple streets. And the result is that you should have more flop bluffs than turn bluffs than river bluffs. Now, if you're a cash game player who's mainly playing 100 big blinds, in single raise pots, you can use the 1/3, 1/2, 2/3 rule. This is a simple rule of thumb that tells you approximately what portion of your range should be value bets on flop, turn, and river. Your static bluff catchers recover their calls when villain gives up. And so if villain is not giving up often enough, your static bluff catchers won't recuperate their calls. And so you should probably start overfolding those, especially if your opponents are too value heavy. The give up percentage, that is to say the proportion of range that someone should give up after bluffing, is approximately equal to the previous street pot odds. So if someone bets pot on the turn with a polarized range, they should give up approximately pot odds of the time on the river, so about 1/3 of the time. If they were to bet, for example, half pot on the turn, then you would expect them to give up about 1/4 of the time on the river. And that's ultimately how you recover the previous street call. And finally, if villain isn't giving up enough, they're unbalanced in some way. So either they're, balanced on the turn, but then they're over bluffing the river, or they're under bluffing the turn and then correctly bluffing the river, or somewhere in between there. But it is impossible to be balanced if they don't have give ups. And so a lot of old school poker theory said, you should just never give up with a bluff. If you're going to bluff, just pull the trigger all the way through. Well, that might be fine exploitative advice sometimes. It disagrees directly with game theory, which says you actually need give ups in order to achieve a balanced range. Check out the articles in the description for more information. I'll post a link there about leverage as well as the Caveman GTO calculator, so you can read that if you want to learn more about these concepts. If you have any questions, if you need something clarified, please reach out to our Discord channel. We'd love to hear from you. And as always, happy grinding.